Uh, the problem with all these video files, your video files are close to 39 gigabytes. Sum total. Some are 8 gigabytes, some are 3 gigabytes, some are 2, depending on your machining time. The length of the video file is huge, and it takes a long time to upload into anything at all. But anyway, I did send, and I did ask for acknowledgement. I did send it long ago, except one, maybe two. Nobody else acknowledged, so I assumed everybody has seen it. So I had to remove it yesterday because my graduate course is also going to kick in, and there's a huge files I have to upload. So anyway, I think I've covered everybody. Now regarding the project 3, yes, you should keep going, and I hope you had time to work on it during the break. You have this afternoon and 2 labs next week and 1 more after that, because your exam is on the 20th of January, which is a Thursday at 4 p.m. and it is an online exam. Okay, so I can send invite to, or I might send the whole class to join me on a Thursday or a Tuesday or Thursday or whatever. So those who want to make use of the time, you are most welcome to do it. Okay, so I would send the invite only about 15 minutes when the web opens. I can't do it ahead of time. Any questions from anybody regarding project 2 or project 3?
When is project 3 due?
Well, depends on how you guys are going to show up in the labs. I would put it as the 19th, one day before exam. It's cutting it very fine because these things take a long time to correct. Okay, for example, project 2. I have spent fair amount of time, even without your reports being in examining all your Mastercam files and the toolpath files, as well as quantifying what would have been the problem in almost everybody's case. So 19th is cutting it fine, 20th is the exam, and the department requires the grades by 27th of January. So fair amount of work to do for me. So 19th is the cutoff date. 19th of
Have
January.
a project 4.
Okay, now let me come back to it. I don't see, normally on this course there have been only 3 projects, which is 1 CNC and 2 PLC. This year I put a project 1 on the CNC and a project 2 on the CNC, hoping that it'll help the project 2 doing the toolpath. And then the project 3 has 2 components, the first part and the second part. So I was too ambitious in putting a project 4, but that's not going to happen. So finish the project 3 in the entirety, project 3A and 3B, and submit it. Okay. Project 3A requires, I'm going to put the rubrics in the course, report requirement sometime tomorrow. You will see you do have to do the truth table analysis, come up with the equations, and then make some modifications to make it workable, and then extend it to 3B. So if you do the project 3, A and B, that's the end. Is that clear?
Yeah, sounds good.
Okay. So,
Sorry, just one more question. In my video, they put a check mark at the end of it. Does that mean that it fit the lamp body?
who are you? Ariel? No? Whom am I
Yeah.
speaking to?
Yeah, it's me.
Yeah, I if you did put a check mark that is coming from Dave, or if there was a check mark, I can tell you I have already evaluated all the fitments, and I am not sure I can tell you by email as to what I have noted. It doesn't mean out of the 13, I would say 1 will fit, 2 and 3 may fit if I do cleanup, manual cleanup. So some have all kinds of other problems. Okay, so I do not know. I got to check my detailed logging Microsoft Word. So I will send you an email. Okay, and also be aware if you look at the rubrics, fitting the base and the lamp is not the be all and end all. Your report is equally important as to how well you document everything.
Thank you.
Okay. So I'm going to resume where I am. I am supposed to cover this part plus one more on robot, but that one more in robot is not going to happen. I will move it to the second course. Regarding the second course, at this point in time, I have 2 people. 2 is the minimum required. From then on, it is going to be clamped to 4 maximum. But I do not know whether anybody from CIMA 1 wants to take CIMA 2. There has been a lot of requests from people who have not done CIMA 1 to take CIMA 2. That's a big problem. So if you want to take it, you send me an email for approval. But I'm not going to let it go beyond 4. 4 is the maximum. And
Sorry,
Yep.
I had heard talk that you were going to run it in the summer. Is that still the case?
It's up to the department to approve it. It's not me. I may want to do many things. It has to be approved by the department because there is always a TA support that has to be provided. For example, in CIMA 2, for 2 people, I am not going to get Matt back. I have to be the TA also by myself. Okay, so yes, I would love to offer it, but it's subject to approval by the faculty. And I have no idea about this COVID problem. CIMA 2 cannot go as online lab. Absolutely not possible. In fact, I made a request for coming term. I am told there is a good possibility it can be online, not online, it can be in-person lab. So I've been assured by the head, I've given them the justification. It is very different from CIMA 1, very long project involving robotics and PLCs and so on. So no online for CIMA 2. Even now I regret accepting CIMA 1 as online because it's given me a lot of headaches. Okay, let's go. I have to finish. We looked at the classification by way of geometry. Cartesian starting with cylindrical, spherical, articulated, and then scalar. Okay. Now I'm going to do classification by control method. The first one is non-servo versus servo. Then there is a classification based on how you're going to program the path. Point to point, continuous, and controlled. Out of which point to point and controlled are exactly similar to what happens in a CNC machine. Continuous path does not exist in CNC machines. It exists only in robotics. Okay, so we'll go over one by one. The first thing that we have to understand the difference between a non-servo and a servo. Okay, so simple example I would give is this. which should be adequate. So I have a motor here attached to a lead screw, maybe through a gearbox. We don't care at this point whether there is a gearbox or not. And then there is a carriage. Okay. Now, if depending on what type of motor this is it a servo or a non-servo? Okay. Now, in the case of an electric motor, if you take a toy motor, when you apply voltage, boom, it keeps going. There is no stopping in between unless you kill the power. As a result, with the inertia kicking in, you cannot stop it at any precise position that you want. Can stop, but it would be off this way or that way by some amount, depending on how fast you're going. But if I use one of those toy motor, like a simple DC motor, okay, and then put a stop at the end, and this is automatically the stop. When I power it, it'll keep moving all the way and hit this end stop, and it can't go anywhere else. So you can quit the motor and make it stop, make the carriage stop here. Then when you reverse the direction of voltage to the motor, the carriage will go this way and will hit the end stop. Can't go anywhere beyond. And then you either visually or by some other means switch off the power. If you don't switch off the power, the motor is going to see what's called as a stalling torque. Stalling torque is current is applied to the motor, but it cannot spin because it's been stopped by a hard stop. So when once it hits the stalling torque, depending on your voltage, the motor will act as a resistor, developing heat, and eventually will burn. Okay, so it is up to you to stop it quick. Maybe put a switch as part of the power supply on either side, like a staircase switch, okay, where you can switch it on or off from upstairs or main floor or whatever. So such motors, if they are used in this case, will become a non-servo where there is no way of controlling any intermediate position. Plus, you do not need a feedback to go from home position to the advanced position. The other example I would give, okay, let's say I have a air cylinder with a piston. Okay, now when I apply air to this side, there are two ports. If I apply air here, this cylinder will extend to whatever it is capable, right? It'll extend always to a specific end stop when I apply air. Now, if I collapse the air and apply the air here, it'll retract. Let's say this is the minimum position. It'll retract. So this is your throw, whatever throw length is. Now, in the case of air, when I apply pressure here, there is no electricity, nothing. It applies the force to the cylinder and push the load to this point, and that's its extreme, and will keep applying the force on the object. If you collapse the air here, yes, that pressure or force is gone, but part is moved to that point. There is a home position and there is an advanced position. Exactly home, advanced. In the case of an air cylinder, well, you're simply applying the air. That's about it, through a solenoid valve. There is no other electricity that is going in. So this also will become a non-servo application. In robotics, this is very extensively used. There are cases which are going to come up in point-to-point application where you don't care about intermediate positions. Plus, there is no path control. In this case, it's all straight line. If it is a circular actuator, when you apply air from here, it moves to this position, 90 degrees, 180 degrees, whatever you set as a dead stop. right? Again, no intermediate positions can be controlled. Here, no intermediate position can be controlled if it is this model that I have drawn. But now I replace this motor with a servo DC or a servo AC and then attach a feedback unit at the back to exactly know the position where the slider is. The same model becomes servo based. So that's the difference between the servo and non-servo. Okay. So I'm now going to open up the servo and non-servo and then go into the three modes of path control. So as you see here, servo is very simple to control. No big microprocessor is needed. No programming is needed. There is a home position. There is an advanced position. You can do it with a PLC or any microcontroller with no exotic program. Okay. Does it have an application in the area of robotics? Well, I talked about transferring parts from an incoming conveyor to an outgoing conveyor. And I gave you the example of sandbags, 25 kilograms. Who wants to lift and palletize? If you're bringing one from Home Depot for home use, you can carry it and throw it into your car and have or somebody else load it into your car. 25 kg is pretty heavy. It's like what the airlines allow as the weight for a suitcase these days. Checked baggage is not even 25, it's 22 kilograms. Okay, so imagine doing this 8 hours a day in loading sandbags after they are filled and sealed onto a pallet for being shipped outside, and you're paid minimum wage. You are going to break your back, no question asked. So in the case of a sandbag, just moving it from one conveyor to another conveyor, no big deal. There is no path needed. Pick it up, lift it up, swing it, and throw it into the other conveyor with nothing happening in between. So, as it says, axis remain in motion until the limits of travel for each axis is reached. Now, if it is 1 degree of freedom, my model shown here will apply. Where is it? Yeah. So home, advanced, that's it. And if I put one more here, piggy bag, I have 2 degrees of freedom. And if I put one more to lift this up, down, in the case of a cylindrical robot, I have 3 degrees of freedom where all axes either have a collapsed state or an advanced state. And you can exercise all three simultaneously or one at a time, depending on the application. Okay, so that's the slide. Yes, only limits are sensed and the motion will cease. Why does it cease? It's because of the end stop, not because of your controlling the motor or the air. But you need to control, in the case of a electric motor, you do have to cease the power or cut the power to the motor, otherwise you're going to lose the motor depending on how the warm heating up goes on, maybe 5 minutes, maybe 10 minutes, okay, something like that. It's like applying the brake on your car with your gear shift in the drive position, and you're applied the brake, but at the same time you're going to press on the accelerator to increase the engine speed. Will it move? Depending on how well you brake, it may not move, but you could be busting your transmission or something else will happen. That's the example. So you got to seize the power. Okay. The non-servo can be absolutely open loop, but it can also be made to a closed loop. So what will happen in a closed loop? Well, if this is a motor or advanced, I put a sensor here and I put another sensor here, and I have a little controller here. Tell the controller, hey, move the motor to the advanced position and keep applying the electricity until this sensor says I am true. That means you have reached the advanced state, and now cut the power off. Okay, so what are you gaining? If it is a screw, it will maintain its position. If it is a cylinder, it may not maintain the position. But this sensor, when coupled to the PLC, will cut the power off, save the motor from getting damaged. Same way, the home sensor will bring it back all the way until the home sensor becomes true. Now, is it open loop or closed loop? Well, depending on how you define the open loop and closed loop, it could be called a closed loop, but with very limited capability. I can control any of the intermediate positions with this method, with only 2 sensors. Now, can I put a sensor which is going to continuously tell me where the load is? Yes, it becomes then a servo. That means you are putting a position feedback. Okay, not so with the air cylinder. Now, if I ask you, why would it be so difficult to control intermediate position of an air cylinder? So, a simple model. Okay, I have an air cylinder that is pushing a load. Okay, and I am applying air pressure here or here. To retract, I apply here, it will retract. To advance, I apply air here. Why would it be difficult? Say it is capable of going up this far, but I want to make it stay right here. And knowing the way the air works, let's say this cylinder is capable of taking up to 30 psi, and I have a line pressure of 120 psi. I can go up to 120, but 30 is good enough because it's let's say this is a small cylinder. So I applied 30 psi. That's the pressure that is applied to this air cylinder, and it's going advanced, and I want to maintain here. Will it stop? No, it'll keep going to its maximum distance. Now, if I come up with a strategy, well, I'm going to apply 30 here, and I am going to also counter by putting 29. That means the net force that is transmitted is whatever that would be out of 1 psi. Okay, so I start with a 30 and I slowly control or do some proportional control, PID, whatever, and take it this far and start applying 30, 29, 30, 29 to keep it in that position. Will it work? Well, you are dealing with air, which is compressible. Do you want to model the compressibility of air for a certain load? Yes, theoretically it is possible. But when you want to implement and do all this complex control, forget it. So it's never done. Even though over the last 10 years, a British company called Enfield is claiming that they can do intermediate position control with air. Okay? In our own university, Dr. Seperi is doing some amount of work in this, but I always question, well, if I want to maintain on a sinusoidal wave, that means this goes oscillating back and forth. You don't call that as position control. No. Okay. I want to lock into a certain position. That's position control. Not possible, not that easily done, but the same principle is applied to when you apply oil pressure, hydraulics. When when your car goes up on a ramp and they push it up with a hydraulic piston, they can control the intermediate position. Where there are more complex control of this inlet port and outlet port, where you can pulsate and control the pressure, because oil, in comparison to air, is a lot more incompressible, and it is possible to control, right? So this opens up to a lot of discussions on these. So in non-servo, no monitoring of intermediate position. Hence, I would call them as open loop. Now, can somebody say, well, I take a air cylinder and its throw is 12 inches or 30 centimeters, okay? And I want to go, I have some application where I can go to 30, but right now I want only control 10. Okay, no problem. Okay, take that cylinder and the piston. It's capable of going this far, let's say 30 centimeters. Now I want only 10 centimeters. There is a paddle here. I put the dead stop here. That means it only goes this far. And I can adjust this, keep adjusting mechanically with hand to increase or decrease the throw. That's what the first statement says, adjust travel length by adjusting the positions. I have to remove this. Coming in the way. And positions. PLC can be used to control this kind of application. What's the advantage? Well, once you start putting path control using servo-based modeling, you need a computer, you need a complex code, you need complex models. As a result, the cost of a servo with path control will become more money, more complex, whereas the non-servo with PLCs or whatever is low cost and simple to execute. And they have a lot of application in the area of robotics. Okay, so also it says some path control with intermediate sensors. Yes, you put a fixed sensor somewhere in the middle and keep adjusting it and let program the PLC, hey, take it this far. Okay, but not possible easily with the air cylinder application. Possible with electric motors. But the advantage of this air cylinder or whatever with no intermediate path that can be controlled is on, off, bang, bang. That's what it is. It's called bang, bang controller. Very fast. And when you drive it to the end stop, which is some hot stop made of steel or whatever, it'll always go to that position. That means its accuracy and repeatability are excellent. Okay, it'll always give you that end position no matter what. So the advantage with the air cylinder and other non-servo, relatively high speed, very accurate, and very good repeatability right through until it starts wearing out. Okay, but you can almost see, now I gave you the example of a sandbag palletization or anything like that. Parts are coming. When the 25 kilogram bag has reached its pickup point, pick it up and throw it into the pallet. Okay, that's it. That's all it's going to do. You adjust all the parameters for transferring the bag with nothing happening in between. Now, can I go and change this program to do something else? Not easily at all. You got to make all kinds of mechanical modifications. Okay, so they are limited flexibility, but they have their own use in the area of robotics, and we will see some of the applications as I'm going to show some videos to support all this. Not possible to do coordinated motion. Just accept it because I'm going to illustrate it with a sketch. Okay. Servo. The control on each axis if it is multiple degrees of freedom, is closed loop. When I say closed loop, you need feedback. Okay, position, velocity, acceleration, all of it is required for the control model. Okay, as a result, when once the word position is shown there, once you have the word position there, tells me any intermediate position can be monitored and locked. Okay, precise motion. Yeah, I want, take the case of a CNC machine. I want to go along the x-axis, 13.475 millimeters, centimeters, whatever, right? Absolutely possible. And can do this along the x and the y and the z in the case of a CNC machine, or in multi-degree freedom, 5-axis. I can even rotate the part by precise amount. Okay, so that's the characteristic of a servo-based control. Velocity, which controls the feed rate in the case of a CNC machine. Acceleration, deceleration. Start fast, go to the steady state, and then decelerate when you are reaching the final position and stop. And jerk, time derivative acceleration. Everything is possible in servo control. Any machine that is based on a servo is capable of doing controlled path, CNC, linear interpolation, circular interpolation, whatever. Continuous path in the case of a CNC does not exist. In the case of a robotics, yes, possible. And point to point. Sandbag is point to point example. Moving from one point to another point without any path control. Everything is possible with servo, whereas in non-servo, only point to point is possible. So, in comparison to non-servo, servo will require a lot more memory, especially when it is going to be continuous path. You can create all kinds of complexity. I can do C-spline, B-spline, NURBS. Everything is possible. Okay. So that's where the servo is going to win, hands down. Okay. You can control the velocity, which is the feed rate. That tells you I can control the path much more elegantly, smoothly, without any jerks. Also, the positional accuracy can be varied by using control algorithm. If a machine is made to work to an accuracy of, let's say, 1/10,000th of a millimeter, I can turn that same machine using positional accuracy algorithm to be good only to 1/10th of a millimeter. Why would I want to do it? Well, by doing so, I decrease the computational burden. That means I can make the machine go faster, but at the same time, I'm losing positional accuracy. There are some applications where you might want to do it, and this happens quite often in robotics. Simultaneous motion of joints are possible. The X and the Y and the Z or whatever. In the case of a servo, I can control it. In the case of a non-servo, I can also control, but I cannot coordinate and make it integrated. In the case of a servo, I can do so. Generally, servo-based controls are more expensive and more complex. Now, I'm going to take the three classifications. I said point to point, the continuous path, and the controlled path. Okay. Now, I'm not going to dwell quite a bit into controlled path because you have already seen it in CNC. Okay. If I take the X and the Y, I start from here, I can go, let's say this is origin. I can go to A. I can go to B. I can go to C, where I am controlling the path to go along here or here or here. Or I can do this, go along an arc starting from A to B, going clockwise or counterclockwise using circular interpolation, linear interpolation. That's what the controlled path would be. It applies to robotics too. In the case of a CNC machine, we are looking at an X and a Y and a Z in a 3-axis. In the case of a robot, we are looking at an X and a Y and a Z as well as the pitch and the roll and the yaw. 6 degrees of freedom. As the number of degrees of freedom increases, the complexity increases substantially. Okay. Now, some of this will come in the CIMA 2. Okay. And I also do a graduate course where I go more heavy duty. Okay. Now, what is this continuous path robot as opposed to the controlled path that I have shown here? Okay, that's what I'm going to explain. Do I have a blank page? No. Okay, so X and a Y. Now, this is what I want to do. I want to go through a path that is shown. It is neither a straight line nor a circle. It's complex. It's got many segments in it. Now, your one route is to, okay, maybe linearize this path, maybe add a little arc here, maybe another straight line here, maybe a little jerks here, and then it becomes complex here. Right? This is where continuous path will come into play. All that I'm going to do is let the robot start recording its position with respect to time. And I'm going to move the robot through this path. Okay, that's the path I want to generate, so I would control the robot manually. Maybe grab its arm and move it. But tell the controller inside, as I am moving, start sampling all the 5, 6 degrees of freedom position and store it. It's like recording music on an analog tape, the old cassette. So you have a recording of the positions with respect to time inside the memory, not on a tape, inside a solid state memory. Now, after I record and close, I say, go back and play whatever you recorded. It will exactly reproduce this path because that's what it recorded with respect to time increments, high-speed sampling, right? So depending on how many points you make it record, the reproduction will be as good as what you did. Okay, so that's where sample the path at high speed and play back using stored data. Okay, where is it useful in the area of robotics? It is no use in CNC machine, or it has no use in 3D printers. It has no use in laser cutters or water jet cutters or plasma cutters. But in the case of robotics, where is it going to come into play? Well, you would have, many of you would have done spray painting with one of those pressurized cans that you buy from Home Depot or Canadian Tire or whatever. Some do-it-yourself at home painting. Just spray with holding the part at a distance. And if you're a good painter, well, you'll get a good finish. If you're not done it before, maybe you'll leave blobs of paint in some places because you didn't control. You held it too long. But take the case of a car, your automobile, thousands and millions of them coming out of the plants. Do they have any blemish that you can spot on the painting on the surface? Then you won't buy it. Okay? But are people painting with a spray gun manually? The answer is no. It's done by the robot. So this is how it happens. If they know what is the make of or the model of the car that they are producing that day on the line, and at the end of the line it needs to be going into a spray booth and painted, they have a complete program for that hood or the trunk or the side door or whatever, okay, which is already collected and stored. They bring that program and let the robot repeat how it would complete the job. Very controlled path, absolutely reproducible from t equal to 0 at the beginning of the day and t equal to n at the end of the day. No fatigue, no complaint about arm being sore, as opposed to a painter will get fatigued. Okay, so spray painting is one example of a continuous path robot. I will show you all this in the video of real world application, which I'm going to show as part of this course. So let me cover whatever that I have put together as my target, and then I'm going to open up. Now, all of this, the controlled path, the continuous path, can all be illustrated using this simple illustration that I've got here. Okay. So what I have in figure 1 and figure 2 are two different type of robots. This is cylindrical. And this is articulated. Okay. So what are the degrees of freedom? Up, down, 1, extend, retract, 2, rotation about the base, 3. So this is 3-degree freedom. I assume nothing else is here. So it's primarily a 3-degree freedom machine. Look at the articulated. The degrees of freedom are identified. 1, 2, 3, 4. So this is a 3 and this is a 4. Totally different configuration and different classification. Now, I want to decide as to which one is going to be useful to me to complete this task. Okay. Parts are either coming or are going to be dropped. Okay. So let's assume the parts are coming on this conveyor, okay, and reach this location. And I want to pick that part. In this case, it is some widget. It could be a sandbag, it could be a cement bag, it could be sugar, who knows. It could be a milk carton. But I want to pick up that object from location number 3. And transfer it to somewhere. We don't worry about where it is going. It could be another conveyor or pallet. If I consider using figure 1 machine, which is a cylindrical robot, and throw this figure out and put this here, it should be in a retracted position. That means this degree of freedom must be folded here. It should be either in the upward position or the downward position, depending on how you want to do it. And it should be in line with the conveyor. That means the angle is 0 degrees, if that is defined as 0. So that machine is sitting here. The PLC, let's assume there is a PLC that is used to detect the presence of the part here. So the PLC tells the controller, hey, not the controller is the PLC. The sensor tells the PLC there is a part, pick it up, tell the robot to go take it away. So what should happen in this machine? It's in a folded position or an upward position. Let's assume it is in the folded position, retracted, and in this. It should move above the conveyor in line with this part. So now comes the problem of not being able to adjust. It's mechanically adjusted to go to position 3. So it's very fixed to do the automation in this task. Moves up, then it extends. This gripper must be open. Gripper is not a degree of freedom. It's either open or closed in this case. Okay, so it extends with the gripper open. Okay, then it has to lower from wherever it is to this position. That tells you the home position must be at this height. And then it closes the gripper, lifts up, retracts, rotates, and throws it on another conveyor that is here. That's this machine. Now, 3 degrees of freedom being controlled could be with a PLC, right? Because there is no path control. Substitute for the same application this machine. Okay, where is it? Where is the home position? Let's say the home position is what is shown in the figure. So when the part arrives, it doesn't have to rotate the base, but it has the ability to rotate this. That means this will fold down, then this will fold up to go into this position. From position 1, it goes to position 2 above the part. Then it coordinates the 2 degrees of freedom to go perpendicular to the part or in a perpendicular direction on a line along the z-axis over the part at number 3. So multiple degrees of freedom are coming into play in a coordinated mode. And then it closes on the part, pulls it up, does whatever you program it to do for a safe path retrieval, and then throw it on a conveyor here. It does the same job, but it does it with a bit more involvement of the different degrees of freedom, more programming involved. The advantage of this machine over this machine on this application is this is more involved, more expensive. This is cheaper, but this has no capability of, let's say, this part changes to a tall milk carton that we are going to handle. That means you have to adjust this position of pickup. A lot easier on this machine. Here it is more adjustments required. So figure 1 is okay. We'll do the job if you don't want to do anything else. This is your life for the rest of your whatever span. Whereas if you are going to change and make modifications to your process, the left one is very limited in terms of its capability to be reprogrammed. Okay, so now these are control point to point versus control using a control path, not the continuous path. Okay, now let's look at this example. We have 2 conveyors, parts are coming on conveyor 1 and have to be transported to conveyor 2. So let's assume you have something that happened on a machine here and then finished part got tossed here and came up here and it has to be transferred to another cell, whatever, which goes. So you know this is the pickup point. You know this is the drop-off point. Okay. Now, how can this be programmed on, let's say, a controlled path machine. You tell the system this is your home position, not home, pickup position. Home is somewhere based on wherever I want to keep it. This is an intermediate position. Why intermediate? I don't want to go straight here and collide with the conveyor 2. Okay? This is the collision path. You want to avoid that. So this is the safe position, another safe, another trip. 3 straight line control path will do the job. How am I going to program? Well, you go to this position, let the robot know the pitch, the roll, and the yaw. Either through a simulation model or through moving manually and recording the position. Then I am not going to exactly move along this line. I'm just going to go manually, and I know the target position is this intermediate. So I moved along this dotted line, wavy or whatever, capturing all my breath and every little uh, blemish in the path that I generated, but I did not record any of these. When once I reach this, I tell the controller, hey, capture, let's say this is X1, Z1, P1, R1, roll 1. Now capture X2, Y2, blah, 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 blah. Store it in the memory. Same way do this, X3 and X4. So I only capture 4 positions. Then tell the system between X1, Y1, Z1 to X2, Y2, Z2 is a linear straight line motion. This is also linear. This is also linear. Right? Even though I moved like this, all of them are thrown out because the controller kicks in now. It generates the interpolated motion between this to fit a straight line. That's the control path. Okay? But if I want to generate this path and I know what is this profile in terms of arc or whatever, same way there are 2 arcs here and I model them, I can make it say between this point and this point, or maybe there is another intermediate point. There is an arc, do the circular interpolation, there is an arc, it'll exactly follow this path if I desire. So it is also a controlled path, but I am modifying the control interpolation by using 1, 2, 3, 4 points. If I desire to do, if there is an application that I need to do, exactly that's what I want to do. Okay. An example would be, if you take your car these days, there are a lot of plastic stuff. Metal is disappearing very fast. You go and have a collision, your replacement of the bumper, nobody fixes anything anymore. The bumper is thrown out, but it could be $1,000, $1,200 because they are putting a new bumper. Okay, they crumble to pieces. About 5 years ago, I went to Home Depot to buy something. As I was pulling out, in front of Home Depot, Walmart, and whatever in not St. Vital, in Canaston, there is huge parking lot, and there is a little bus lane at the end of it, parallel to Canaston. So I came up to the stop sign, and then I pulled into the bus lane, and I was coming out, taking the bus lane. At 30, you can't do anything more than 30. And somebody, a big family, 2 or 3 families, who probably had dinner in Swiss Chalet, and one of them came out of the parking lot without observing the stop sign. They came into this stuff, plummeted into my car. That's the first time I had in my life the airbag deploy. And the car was only 3 months old. It was a Mazda CX-5. The damages on the car, they fixed it, were close to $4,800. Right? So, why did I bring this? The plastics, welding is no longer a major application in automobile industry. It's pouring glue, epoxy, whatever, bonding things together, panels. Robots are used very extensively where you may have a complex path like this. Okay. Now, how comes the continuous path? What's the difference? Okay. 1, 2, 3, 4. You want a perfect straight line? Use the control path. I'm not using a perfect straight line there. Now, if you want to have a continuous path where whatever wiggle jiggle that you produced must be reproduced, okay, or it could be like this. You want it? You record at a high speed all the motion data points and make it reproduce. So this is a magnified section of many points stored in this little. So you are going to have millions and billions of points stored depending on the complexity. So in a continuous path, you simply drag the robot from one position to another position with a desired path and let it store enormous amount of data points. Then when it plays back, it's like playing a music from an analog tape. It simply reproduces, right? But it needs a lot of memory to store these enormous points. It does not need memory to do execution of controlled path, right? So less complex, more complex, more memory. Well, I wouldn't say less memory. It needs memory to do something else, but the data memory is less here. Okay. Now, what would be an example? I told you about spray painting. So if you have a panel that you want to spray paint, like the hood of a car, which is before assembly is painted, let's assume, and it is coming on a conveyor dangling, what you would do is to have an experienced painter teach the robot exactly the way he would paint if it is manual operation that will satisfy all quality control. So one time only the spray painter comes into play, which you are going to see on the video, and it's recorded and reproduced from day to night. If it is 3 shifts or 2 shifts or whatever, the robot is not going to complain anything. It's simply reproducing what the painter did. Okay. Now, in terms of programming, there are a number of different techniques. In the case of a continuous path, possible to use simulator. That means there are 2 robots, or it's the same robot. Used to be 2 different machines. One is the actual robot. Let me show the picture right here. This is the actual robot. And this is a scaled down version of the same machine, but no motor or nothing. They only have sensors at all joints. Okay. So scaled down. So you use this machine, just grab it with the hand and program it. And then only the position goes to the controller, and this machine will reproduce whatever you did. Then there is a scaling factor that is applied. This will reproduce what you need to do. This is called walkthrough or physical simulation using a mock or a dummy robot. Okay. There are a number of different types of programming: teach mode, walkthrough, computer languages. Now go back to this sketch. Teach mode. 1, 2, 3. You take the robot to precisely to these positions. I mean, we don't care whatever that happens here. Start here. Tell the machine, this is my starting position. This is my end position. This is my start position. This is my end position. End position. Right? Then tell the system, linear, linear, linear. And whatever you did here is all gone. It will perfectly fit a straight line between this. So that's the teach mode, where you teach the machine, or you're teaching the machine to go through a path and then put path control. Walkthrough is this. You are dragging the machine and making it learn the path that you did. Computer languages or robots have teach pendant. Okay, you take the pendant and program, or you have simulation languages. Okay, like Mastercam's simulation, where you create a path and then simulate, and then let the robot be transferred the control program. I am going to dwell on these a bit more after I complete this section of some projects that I did for local industry 2 years ago, and I have done many other projects. Now, in the case of a robot, in the case of a CNC machine, all that you're doing is metal cutting. In the case of a 3D printing, all that you're doing is producing parts using printing technology. In the case of a laser, you're cutting parts, right? Water jet cutting, similar story. Whereas in the case of a robot, it can do many more. I can take the robot and use it as a polishing machine. Like, look at your stainless steel sinks. Yes, after it comes out, they are polished to a mirror finish. It used to be several people sitting on a line and taking a rubbing compound and polishing it. Not anymore. These are all done by robots. Grinding. Okay? If you produce parts from a CNC machine, well, you may not get the desired finish on the surface of the part, or you may be left with what's called as a burrs on the sharp edges, which need to be removed. This is the project I did with Magellan. Now used to be Bristol Aerospace. Okay, so before I forget, what exactly was Bristol's problem? I will refer to them as Bristol because when I did, they were called Bristol Aerospace. Bristol was subcontracted by Boeing to make the spars that go in the wings of aircrafts. They are support structures, and they are produced on aluminum using CNC machines. So when the parts come out of the CNC machines, all the edges have to be rounded. The specification that they gave me was 30 thou rounding. So after the parts come out, people manually were rounding it off with chisel, or not chisel, with files and so on. Right? Why should it be rounded? When these parts go into the wing at the highest, not highest, at high altitudes, the aircraft wings are not inflexible. They do flex quite a bit, sometimes as high as 6 inches tip to tip. Okay, so if those parts, these are all from what I heard from them, if they're not rounded, it produces sonic resonance. As a result, the premature failure may happen. So it is the military spec regulation that they have to be rounded. So if the parts came out of the CNC machine in, let's say, 2 hours, people were grinding for another 5 hours. Who knows? Okay, they wouldn't give me the exact numbers. So I was asked to see how it can be automated. Yes, I walked in, did a 2-year project with a student of mine. We completed the project. We used a robot to do the same grinding. Uh, the 5 hours, 6 hours of manual grinding, polishing was finished in 13 minutes. Okay? So there is not even a question about payback period. It would just hands down win, no fatigue, no coffee break. The productivity increased substantially and it was implemented. Okay? Unfortunately, the student who worked with me and myself, we knew everything that we did. Nobody was following from Bristol. So when the student finished his studies, I told them the only way you're going to continue is to hire him. But they kept dragging their feet, and the student disappeared to take up a job with GM in Michigan. Lost. And whatever president who came by next decided Bristol doesn't need any automation, so sell the whole damn stuff and sell it for scrap. So the robot, everything disappeared. Right? Utter shame, but that's what it is. Okay, that's an example for a control path. Welding, very intensively used in many other places, not so in automobile industry. Could be spot, could be arc. I don't know how many of you have done welding. Anybody? I'm sure those who are in SAE or other chapters would have had some chance.
Yeah, I
Okay. Now, there is a big difference between a spot welding and an arc welding. The minivan that came long ago had 3,254 spot welds on the body. Not anymore. Okay. So, Ford and GM, I'm talking about 20 years ago, jumped into robotics because this took a long time, okay, to do spot welding. They didn't do their homework. They bought enormous number of robots based on whatever somebody told them. It took them about 2 years to find that robot did not weld half the joints. It's not the robot's fault. Okay? They didn't know how to program. So they sold the entire, not sold, they donated most of the robots to universities and said, you guys figure it out why this problem is. So many universities benefited in United States. Okay? So everything was brought back and the robot was made to do those spot welding more reliably. Spot welding requires a point-to-point, PTP, because you take the gun, hold, and lock onto a spot, boom, you're done. Whereas an arc is a different beast. The example I would give is welding the seam of a pressure vessel. Could be curved, could be straight line, where you are doing a seam welding between the two surfaces. If you have done spot welding, you don't do spot welding with hand, you take the spot welding gun, just apply heat and point. Whereas in seam welding, you got to take the gun and go along a line or an arc. Weaving. Weaving is important. That means you're making a little oscillation of your weld gun. That is also a parameter. Very easily controlled in the case of a robot. Not that easily controlled by a novice welder, but an experienced welder will control it reasonably well. With the eye, you can find the difference in terms of a poor, less desirable weld or a perfectly welded. You can't say much. Only when you do non-destructive testing, you will figure it out. Whereas robots have the parameters built into them. You adjust the current, you adjust the weaving pattern, and you adjust the feed, and everything is controlled, including the wire feed. Speed is controlled. So welding is a good application, robotic application. Plus, in addition to them, you also use the laser and seam finders to find and do advanced tracking. So there are some cases where you cannot justify application of robotics. Okay, but who wants to sit inhaling fumes or whatever in a welding shop or spray painting? Hands down, should introduce them, save the humans out of those hazardous environment. Okay, so here is a robot that is hung upside down from the roof. It's an articulated configuration, and you see a car body panel. The purpose of this robot is to pour the tiny little adhesive along the seam, which is a control path, and then take the panel into the metal door and apply pressure to seal it. Okay, so in the case of spot welding, right here, that's the car body. The robot is on a 7th degree of freedom. It can go along the entire length of the car. It'll do the spot welding here, spot welding here, spot welding here, spot welding here, whatever. Okay, be done. There is no path control that is needed except point-to-point application. But what is used here is a 5-axis. I have this machine in my lab, a 5-axis robot made by ABB, ASEA Brown Boveri. Okay, so auto industry, as I keep saying, are a major consumer. Not anymore. Other people have taken over. Where the laser vision-based robotic applications are becoming more. Okay, welding, grinding, deburring used to be a common application in the area of automobile industry. Because of glue and plastics, that has decreased. Used to be 87% of the robotic application were there. Now it's dropped to 8% in automobile industry. Okay. Metal casting, drilling holes, nut and screw driving happens all the time in automobile industries. Piece of cake for robots these days. Okay. Then the use of RCC considerably helps the assembly task which a human does with dexterity, but machines have difficulty. So RCC are used. Part handling, that means loading machines. Transfer, the sandbag is an example. Palletization, transfer, sandbag, cement bag are all examples. Okay, are also used in robotics. Okay, I guess my alarm says time up. Okay, next class I will finish this section and I will move on to a few things that I have omitted in the PLC. I'll bridge it and then show some videos. Okay, so any questions? You may have questions about your exam that the university is not permitting in person in majority of cases. So it's an online, which means it's a totally different ball game for me. With all of you are going to have your notes, everything in front of you. So there will be less that you can extract out of your notes, more out of applying the principles of the notes. I'm not even gone there yet. I'll have to think about it and let you know. Okay, any other questions? Not any other questions? Any questions?
I have some questions.
Yes.
But they're kind of personal about my project too.
Yep.
Uh,
Okay, you can. You should stay.
yeah, I'll stay.
Anybody else?
I just have a question regarding the WindLoader, like the program.
Yep.
I still can't access it. It's still giving me this error.
I said, Trevor, you should send email. Trevor, I have nothing to do with. A few others said yes, but Trevor sent me an email yesterday. He's back as of yesterday.
Okay.
He says it's all working. And one or two who's complained that it's not working is working because during the break, all this resetting, whatever, didn't happen. And now it is happening. It has happened. He says it's working. So try it out.
Okay. Sounds good.
Anybody else? Okay, I will send